So we're going to keep talking about virtual memory. We talked about last time this fun thing. Remember, we talked about a few page replacement policies. And then there was this, and we talked about FIFO. And FIFO is really simple. It basically takes no accesses or program behaviors into consideration when it's trying to decide what pages to evict. It just has a FIFO, puts new pages on the back. When the page reaches the front and it needs to evict a page, it just chooses the page on the front, regardless of any other details. So pretty simple. It had this fun characteristic that adding page frames would sometimes cause the page fault rate to go up, which is weird. It turns out that you can actually design accesses where, as you increase the number of page faults, the access pattern actually causes the fault rate to go up. You can also, you have various situations that can occur like this. So it's really bad too. Ours went from 9 faults to 10 faults or something like that. But it turns out that you can actually get a huge increase in the fault rate by adding frames to the system, which is disturbing, I think is a good word for it. So anyway, that was very anomalous. And so we started talking about other policies, and the best one that could possibly exist is we call optimal. And basically that's the policy where we evict the page furthest used in the future. Because if it's the furthest used in the future, it's the one that we, every other page in memory we need sooner than the one that we decide to evict. And so this is going to reduce the number of page faults to a minimum. Of course, like I say here, the problem is that it's impossible to implement because you have to be able to predict the future. So basically what we do is we try to emulate the optimal policy in various ways. And there's some really interesting approaches. We're only going to talk about a handful, and still today's going to be full of page replacement policies, so we'll talk about a bunch. But there's even new ones that have come around in the last maybe decade that are really clever and innovative and come up with ways of getting even closer to optimal. Okay, so one approach, of course, the obvious one is to use the past to predict the future. This is generally what we do. Same thing with shortest jobs first. You guys actually saw a little bit of that with the 4.4 BSD scheduler and, doing your whole, what's my process's CPU usage behavior, and you use some kind of exponential calculation to approximate that. So LRU is also an approximation of the optimal policy that uses past behavior instead of future behavior, which is kind of interesting because, like I say here, LRU is if you were to apply the optimal page replacement policy to the reversed page access string. So that's kind of an interesting little detail of it. But basically, we have to find some way of implementing this, and it turns out to be the challenge. So LRU is good. It doesn't exhibit this anomaly. It's hard to implement. And when I say it's hard to implement, what I mean is it's hard to implement in a virtual memory system where you're basically at the processor level, you're at the hardware level, you're at interrupt levels in your operating system implementation. And we'll see why. It's easy to implement LRU in a file system cache. It's easy to implement LRU in a database buffer cache. In fact, that's what NanoDB does. It's not that hard. But the problem is that it actually requires too many resources to implement at the level that the MMU operates at. And so we'll talk about some of the details with that, why it turns out to be so difficult. Okay. It really all fundamentally comes down to this thing that we have some data that we need to manipulate on every memory access. So two possible approaches generally that you could use. One is to have some kind of clock implemented on the processor that you use to actually record the time of every memory access. Okay. That's pretty easy. You could either keep track of it on a per instruction basis, or if you wanted to be more clever and have your clock advance more slowly, then maybe you only advance it on memory accesses. And so your page table entries would be extended to now contain the time of the last memory access, whether it's a read or a write or I load an instruction to execute, something like that. And so every time an access is performed, obviously the MMU is involved, so it updates this value that's stored in the page table entry. And hopefully you already see that there's a number of issues with this because I have to have a counter that's large enough to be useful. And if I have this counter thing that the MMU is updating, then now my page table entries grow, which means my translation look-aside buffers grow, which means they get slower. And, part of having a cache is that sometimes I have to evict blocks from the hardware cache, and that has to go hit memory, so that access becomes slower. Everything slows down when I do this. The other issue, when I evict a page, now I have to scan through all my pages to see which one was actually accessed furthest in the past. Order n, but hey, n is getting larger and larger as we have more and more pages in our memory. So this also is kind of pretty lame. Okay. Yeah, so like I say here, the TLB would help a little bit, but TLB is going to get slower if we increase the size of the entries. And, so we still have some issues with this, even though TLBs will somewhat mitigate this approach. Okay, so this is one idea. We could go ahead and add a counter and use that for doing our thing. Okay, the other option is to have the hardware manage a queue, which is interesting because now we're talking about hardware managing complex data structures. So far, our processor has been pretty simple, and the most complicated data structures we really need for our processors are arrays, right? I have an interrupt vector table or an interrupt descriptor table I index into. I have global descriptor tables and actual local descriptor tables as well. I index into them. It's really simple so far. I just have arrays, but now we're talking about having a queue. And basically, when you access a page, the MMU would move it to the front of this queue. Okay? And so that happens on every page access. How fun and exciting is that? When you have to evict a page, well, that's now much faster because I don't have to linearly scan through all of memory. Now I just pull the page at the back of the queue. That's the one that gets evicted. And like I say, it is unappealing in the same way that the counter approach is unappealing. It just has different problems in different areas. So choosing a page to evict is fast. That's nice. I have to do a few memory accesses to modify the queue that the processor is managing. But hey, that's a lot simpler than scanning through the many pages that might be in the memory. Accessing is a lot more expensive because now I have this queue that I have to update every single time. Okay? So like I say here, most accesses would incur linked list manipulations. Maybe you could be really clever and say, well, as long as you're within the page, we really only care about accesses on a per page basis. So maybe the processor could be really clever and say, oh, the last 19 accesses have all been in the same page, so I don't really need to update the queue because I updated it on the first access to that page, something like that. But, if you have a singly linked list, I have at least 2 pointers that I need to update, I think. I don't know. Maybe you could get away with just 2. Maybe you'd need 3, depending on how you do it. So you have to manipulate this linked list, and that's going to be expensive. So the upshot, given that we basically have these 2 approaches that we could use, is that LRU in hardware is too complex. We can't do it. And so most of the time, these virtual memory systems don't rely on LRU as an approach. Now, again, like I said, file system caches are great because, hey, you've got all of your accesses are going through read or write, and then they enter the system call so you know what pages are being accessed. That's really easy. Same thing with the data structures. The operating system is implementing that, so it's not a big deal. And your read or write is going to be tens of millions of clocks or maybe hundreds of thousands of clocks if you're using a solid-state drive. So it's okay to waste a little bit of time to implement a more clever replacement policy. But in hardware and virtual memory, it's too slow. So there's many different policies that people have tried to emulate LRU, or again, the goal is to try to come close to opt as opposed to LRU. LRU is not the best implementable policy. Actually, there's a number that are even better. But anyway, there tend to be bits in the MMU's page tables that it will update for you. And it's kind of interesting because we have 2 bits that we mainly care about, accessed and dirty. These are set by the MMU. They are never cleared by the MMU. It's up to the operating system to decide when to clear them. So the MMU sets them when you have a write to a page and the dirty bit is set, or when you have a read or a write to a page, the access bit is set, and then the operating system can decide when it wants to clear these bits. And so page replacement policies could look at these bits and infer various details based on the values of these bits. And so there's a number of policies that you'll see. One is not frequently used. I mean, the policy's name is not frequently used. I don't know how frequently the policy is actually used. But anyway, the idea is that you have a counter associated with each page, and on a periodic timer interrupt, you go through, and if a page's access bit is 1, you increment its counter. And then, of course, you see the access bit is 1, you just clear it, and you go on. So basically, this is all you do for not frequently used. And when you want to evict a page, you choose the page with the lowest count. Okay? Now, this is still going to have the issues that we talked about with LRU. You still have to scan through a whole bunch of pages, so you have to think about those kinds of implementation details. But the idea is that we're approximating this by checking on a periodic interrupt as opposed to on every single memory access. So that's the idea behind not frequently used. Now you'll notice also that it's called not frequently used, not recently used. And if you look at this and think about it, you realize that that counter is really capturing frequency of access, not recency of access. And so this is actually doing something slightly different than LRU. It's looking at frequency information, not recency information. I'm going to mention that a couple of times in this lecture because it actually is kind of important. The big issue with NFU is that the frequency information is not forgotten over time. And so you can see that this is sort of a limitation. If you have a situation, for example, where a page is accessed a lot initially in a program's execution, and then you're done with that page because you don't need that information anymore. Well, that page's counter might be really large, but other pages are going to have to get their counters high enough before that page will actually be evicted. So this is kind of an issue that you may actually have NFU page out stuff that you actually want to keep using for a while because there's other pages historically that have very large counters already. So that's one issue that you have. So aging is another policy that's similar to NFU, but it's cleverer. So it actually incorporates some kind of aging mechanism so that you really only consider recent frequent access, if you will. So NFU is frequent access over the entire history of the program execution. Aging allows you to consider recent frequent access. And so you'll see that it actually combines recency and frequency in a very interesting way. So we have a B bit value. You may have recognized this from a CS24 exam because I like to sometimes come up with other policies to make it more interesting. But anyway, the OS has a periodic timer interrupt just as before, and it basically scans through all the pages. Every page has this age value associated with it, and what we do every time we visit each page in the timer interrupt is we shift that page's value right 1 bit, okay, which means the bottommost bit falls out of the value and everything shifts over. And then basically the topmost bit that we shift in is the current accessed bit value for that page. If it was accessed, then we shift a 1 in. If it wasn't accessed, then we shift a 0 in. That's all there is to it. And then, of course, we clear the accessed bit if it's already set. And it turns out that if you do this, then pages, and again, this is like probably not stated very well. Pages with more recent accesses will have a larger value than pages with less recent accesses. What does that mean? Is this actually a good approximation of least recently used? Well, kind of, but not really, because this B bit value is kind of a window. And if you have a page that's accessed in every step in that window, then it's been accessed very frequently in the recent past. So you could think of a real approximation of LRU would be to only consider the topmost 1 bit in this age value. But the aging policy considers all of the bits in the recent history. So it's kind of, again, mixing recency and frequency. Okay, so let's look at this. I have an example, a memory reference string, which thankfully we don't have to think about too much because it looks very tedious. Okay, and so you have this periodic timer interrupt, and you look at all of the accessed bits, and you look to see what has been accessed since the last timer interrupt. Has it been accessed multiple times? We don't know. We just keep track of whether it's been accessed at least once. And so this would be the current, so that little block is the set of accessed bits from the page table. And so this would be the current age values in base 2 and in base 10, just so that it's easy to keep track of. And so you can see that pages 1 and 2 have been accessed, 3 and 4 have not, 5, 6, and 7 have been accessed. The larger values represent pages that have been accessed more recently or more frequently as well. We'll see that as we go through this. And the pages with the lowest age values have not been. So they would be good candidates for eviction, we think. Okay? So then we have another timer interrupt. We look at, and remember, all those ones were cleared at the previous timer interrupt. So now page 1 has been accessed again since the last timer. Pages 5 and 7 have been accessed. So 1, 5, and 7 get a 1 bit shifted in, and everybody else gets a 0 shifted in. Okay? So that's kind of the idea, and you can keep playing this out. I have a couple of more things that you can look at. Let me see if I have any good examples here. Yeah, so look at pages 2 and 3 in the rightmost box, bottom right box, for the age values. You know, again, if you were thinking about pure LRU, these have both been accessed recently. But we actually don't consider only recency, we also consider frequency. Page 3 has been, I'm sorry, are those values actually correct? I just realized page 3 is, anybody really good at binary? Off the top of your head? Those values don't look quite right. Because page 2 has more 1 bits, it should have a higher age value than page 3 does. Okay, so I'll have to look at that. But anyway, if a page has more 1 bits, it's going to have a higher value. So you're actually looking at frequent accesses in that window as well as recent accesses. Okay, so that's the kind of thing about the aging policy. It's kind of an interesting blend of the two. I am definitely going to have to look at that value. 208. So yes, so page 2 should be 208. Yeah, it looks like when I have a copy-paste error, so teachers make them too. But anyway, yeah, so I just accidentally copied that value over. So, okay, so that'll be 208 when I upload the slides. Thank you. Any questions? So aging is a really simple policy to implement. It's one that... and like I'll talk about this in a second. So aging is a very simple policy to implement, so you actually see it relatively frequently in systems. It's a clever approach that gives you a pretty decent result. So I say here the main difference between aging and LRU is that aging has a lower resolution on its recency information, but really the biggest difference is that aging also considers frequency, which LRU does not. So I would say that that's even a bigger difference. Yeah, it is very common, you know, because you don't have a whole lot of bits for recording this information. You have a lot of pages that end up with the same age value. And so LRU would be able to distinguish between those, but aging does not. And the same thing if you have pages with an access value of 0, you know, or I should say they have an age value of 0. Again, LRU would be able to distinguish between those. And so what you typically see on these systems is they do quite well with just a small number of bits. Okay. Anyway, so that's an interesting approach. And obviously you wouldn't want your timer interrupt to go too frequently, or else that would slow down your system as well. So you have kind of a coarse granularity that allows you to make pretty decent decisions. Okay, any questions? So that's aging. There's a lot of other policies that use this access bit. They're kind of interesting. One is FIFO. We can actually take FIFO and make it a little bit more clever by having it also look at the access bit of the page at the front of the FIFO. Remember, the original policy is when the page is at the front of the FIFO, it is the candidate for eviction regardless of what the program is doing. So we can actually change this so that if the access bit is 1 of the page that we want to evict, then we won't evict it. We'll move it to the back of the FIFO. Okay? If the access bit is 0, then we go ahead and evict it. So it's a very simple little tweak, and now we have a policy that is actually significantly more clever than FIFO. Okay? We call it second chance because every page is given a second chance. And of course, there's some anomalies that you have to sort out because when you first add a page to the FIFO, if you think about it, what would have made a page be added to the FIFO? Well, you had a page fault, and so you need to page in the page, and then the fault handler returns, and the program attempts to access the page again. That succeeds, so now the page's access bit is 1, and so it gets to the front, and hey, look, its access bit is 1 because it was accessed at least once. And then, so basically what you're saying is every page gets at least one second chance. Okay, so that's kind of the interesting thing about second chance. Little implementation detail there. Okay, so here's the question. What happens if all pages have their access bit set? Well, that's a pretty easy thing to understand. Access bit is 1. Let's clear the access bit, put it at the back of the FIFO. You know, all of the pages go through in order like that. And on the second pass, we just choose the page that was at the front of the FIFO at the beginning, because it was the first one with its access bit to be cleared. So you can see that when second chance has a situation with heavy memory load, then it basically degenerates into FIFO. It has a lot more CPU usage to get the same crappy policy, yeah. Yes?
Do all these policies guarantee that all the pages will be used first before any pages are paged out?
So that's an interesting question. Do we guarantee that all the pages will be, and I'm presuming by that you mean page frames, right? Yeah, so are we guaranteeing that all page frames are utilized before we start doing these crazy things? The answer is actually a lot more varied than you'd think. In general, you can think of it as yes. If we have an available frame, let's just use it. That's the fastest thing we could possibly do. And so typically you don't implement these behaviors until you actually have no more frames and you have to evict somebody. The situation gets a lot more nuanced, though, in how real operating systems do these things because of a couple details, one of which we'll talk about, which is that operating systems frequently try to aggressively reclaim page frames so that they just have an available frame pool to choose from all the time, which means that you might apply this kind of policy in the background, not when you need to, but when you have available time so that you can actually get a pool of available page frames. And the second thing that's really interesting about this is that pages that are evicted, we actually, most operating systems don't just straight up evict pages when you decide that this page is worthy of eviction. What you do instead is you add it to a pool of candidates for eviction. And so they're unmapped from any process, but you might still have a page fault against that page that is a candidate for eviction. And if you do get a fault against that page, well, you don't need to reload it because it's already got the data in it. You just remap it to the process again. So that basically allows you to revert bad decisions by paging algorithms. Okay? So if that didn't make total sense, then we'll talk about it a little bit later in the same lecture. But both of these things basically mean that you may be applying these eviction policies at other times besides just when you don't have any frames. And anytime a process needs a frame, you may actually have a pool of available frames to choose from. So those two things together are a much more realistic picture of what actually goes on under the hood. I hope that answered the question. Any other questions? Okay. Let's see. Clock. So second chance, as was pointed out, is a slow, beastly implementation, and it turns out that clock is a much more efficient implementation. I can't remember. Is this one that has to be done in CS24? It used to be. It used to be that you had to implement clock. I don't know if you still have to implement clock. But clock is basically an implementation of second chance that doesn't suck. Okay, that's, so if somebody says, well, what's the difference between clock and second chance? Now you know. They implement the same policy. They just, clock is a lot more efficient. So basically you have all pages, and again I should probably be more specific and say that all frames are maintained in a circular queue. I should say frames with pages in them would probably be the right way of saying it. And you have a clock hand that points to the current head of the queue. Okay? So that's the one that you would consider for eviction if I have a situation where I need another frame to use for something else. So that's where the clock hand points. And so when the page has to be evicted, I look at the page that the clock hand points to. If the access bit is 1, then I clear the access bit and move the clock hand forward. Okay. So now I'm not moving nodes in a linked list. Now I'm just moving the pointer into the linked list. That's a lot more efficient. And of course, at some point, if the clock hand sweeps through all available pages, because all of them have been accessed, then I get back to the beginning of that linked list, and the page now has its access bit cleared. So again, it degenerates into FIFO if everything's been accessed. Okay? So I suppose what I would say is this still has pretty heavy CPU requirements, but at least the memory access overhead is a lot smaller than second chance would be. Okay? So that's another one that's pretty straightforward. NRU is a nice simple policy, which I really love. Again, this one also frequently appears on CS24 exams, just because it's so simple. So you have the accessed and dirty bits. And again, you have a timer interrupt scanning through pages, and the access bits are cleared, which is kind of interesting. So it's clearing access bits. It turns out that it's also doing something else. But what this means is that we might end up with pages that are accessed and dirty, accessed and clean, because they haven't been written to. But now I can also have not accessed and not dirty, and I can also have not accessed and dirty, which is a weird situation. But really what it is just that the interrupt has cleared the access bit, but the dirty bit is still 1. See, the dirty bit is just telling you that at eviction time, you need to save the page's contents somewhere. And so we use this pair of bits to classify pages. Okay, so we have not accessed and not dirty, not accessed and dirty, and then we have accessed and not dirty, and accessed and dirty. And basically what we can do is use this classification system to choose pages to evict based on how expensive it will be for the overall system. Okay? Now it's interesting because you could argue in various ways whether or not classes 1 and 2 should be reversed from the way they are. NRU happens to pick this order. Okay? So not accessed, not dirty. Those are the cheapest pages to evict. They probably won't be accessed again. That's a guess, you know. But they're not dirty, so I don't have to save anything. Okay, same thing with not accessed and dirty. Well, it hasn't been accessed. I probably need to write it back anyway, so let's go ahead and get that started. It's more expensive. Class 2 is accessed but not dirty, but we're going to assume that evicting that would be more expensive than Class 1 because it's been accessed. So it probably will be accessed again soon, and the whole process of reloading that page may be more expensive than just saving the page that is dirty. So that's the reasoning behind classes 1 and 2. And then class 3 is obviously the most expensive to evict because A, I have to save stuff back. B, I'll probably have to reload the page really quickly. So that will probably incur the most disk accesses if I evict a class 3 page. Okay? So basically, the hard part is keeping track of these classifications. And so again, your timer interrupt would probably do that. You know, keep various linked lists or collections of pages that fall into the various classes. Because you could always tell as your timer interrupt is traversing these classes, you know, or traversing all pages, you can just look at accessed and dirty and update your collections. Okay, so that's another interesting approach. Pretty simple conceptually. Okay. Any questions? All right, so that's NRU. Okay, so remember now we have LRU, NRU, we have least frequently used, which we talked about first, so LFU. I think there's even an NFU policy. There's just tons of different policies, and they all, unfortunately, have been given 3-letter acronyms, so it's easy to have collisions and try to figure them out. Okay, Working set. So another policy that has been considered, and it's a pretty interesting one, is to look at the working set of a process. The working set of a process is the set of pages that it's actually using right at that point in its execution. It may have a whole bunch more pages, but it's not accessing them, so it doesn't actually need them in frames. Those can be paged out. It's just the working set that needs to be in page frames at any given time. And the general behavior of programs, as has been experimentally measured, is that its working set changes slowly over time. So you may have certain pages that are being utilized heavily because they may contain part of the code that's being run. You may have sections of data that are being accessed a lot. Those pages need to be in memory. And then you have other stuff that doesn't need to be loaded. And as time progresses, pages will enter the working set and they'll leave the working set. Now, does it stay the same size? That's a really good question, and I think that probably you would find that in general it changes. The working set size changes over time as well. Okay, so just the presumption of this approach is that the replacement policy should try to keep pages that are in the working set and evict pages that are outside of the working set. Okay? Because if it evicts pages that are in the working set, well, then I'm causing more faults in the future. So you kind of have this thing, if you overestimate the size of the working set, it's kind of expensive because you'll use more frames than you really need, but at least you're not generating faults. Faults are slow. But if I try to estimate and my working set estimate is smaller than the actual working set, then I'm going to increase the page fault rate pretty badly. Okay. So here's the question, can we actually approximate this working set? Again, we use timer interrupts to try to figure out what the current working set is. So we have this parameter tau, which we can tune. It would be pretty interesting. I don't think the working set policy that we talk about actually tries to tune tau, but you probably could come up with a way of tuning it based on the faults that you actually see, and you could have tau be on a per process basis. So you could come up with some pretty clever approach using this kind of thing. It turns out that there's actually much easier approaches that are very clever and do a really good job. But this was an interesting area that was explored. Okay, so you have interrupt at T1, and you look at all the accesses that have occurred within tau of T1, and basically anything that has been accessed you consider to be part of the working set. So you want tau to be large enough that you fully capture the working set of the process. So you can see that based on our guess of tau, we're presuming that our program's working set is 1, 2, 5, 6, and 7. Those are the pages that are part of the working set for this program. Later, at time T2, we look at the memory accesses, which again we are captured in the accessed bit values. Then we can say, well, now the program's working set is 1, 2, 3, and 4. And you might eyeball this and say, well, yeah, that seems like a pretty good guess, but we don't know what the ... is, so we don't really know for sure. But you can see that the program's accesses do change over time. And so maybe we can try to keep those pages in memory, and ones that are outside the working set we can get rid of. So that's what WSClock tries to do. And it's kind of a complex policy, and it's kind of fun to look at, partly because you start to realize how sometimes these page replacement policies are just kind of Frankenstein's monsters of bolted together strategies and techniques for dealing with this. And so you'll see that there's clock, there's LRU, and there's this working set idea, all kind of fit together in some way. Yeah?
Is there any reason that there's not a policy that relies on the user process to tell the OS about what it should be doing?
Well, that's a really interesting question. I'm not sure that there's any policy that takes user process input for page eviction. But page allocation, which we've not talked about yet, is something that operating, like Windows is a really good example. It takes input from user processes to say, this is my preferred working set range. Like, these are the numbers of pages I would like to work with in memory, and then Windows actually tries to use that in page allocation decisions. Now, page allocation is how many frames does this program get to keep in memory. That's different than eviction. And Windows will try to squeeze things if processes are, if there's too many processes and it doesn't have enough frames for everybody. But that's the only place I've really seen user process input taken. Yeah. Because I think the reason why is because the OS just kind of watches program behavior to try to make those decisions.
Yeah, I was just wondering because a lot of times in coding it's easier to just watch the end results, but it's often more efficient to try and do something at compile time.
Yes, and so I think that I don't know. Yeah, that's an interesting question. Do you rely on a programmer to give you that input, or can the compiler infer things? I really don't know. That's an interesting question. But yeah, like I said, the only place that I'm aware of is in the page allocation side of the picture. Okay, so we'll look at this real quick. So again, we have a virtual clock. You can see the timer interrupt is getting its workout here. So we have a virtual clock for each process. And that might be the amount of time that the process actually spends on the CPU. Again, you all probably have seen this very frequently by now, but in the timer interrupt code, there's a little bit of code that keeps track of, am I in user code, am I in system code, but we basically can keep track of how many timer interrupts have I seen, and you could use that as a simple clock for your process. How much time has it run? And so you can basically use that to figure out the tau. How far back do you actually want to look at memory accesses for that particular process? Okay, so we have a circular queue, just as with clock. You can see clock is in the name, so we have a similar approach here. And pages also have a time of last use. Now, what is that time of last use? We don't really know it, but it's an approximation, and we can approximate it by looking at pages in the timer interrupt. So basically, we iterate through pages, and when we see that a page's access bit is 1, then we set that page's corresponding time of last use to be the current virtual clock value. Okay? And then we clear the access bit. If we come across a page and its access bit is 0, we don't do anything with the time of last use because it doesn't look like it's been accessed since the last interrupt, and we go ahead and move on to the next page. So you can see that the time of last use is going to be really approximate, and it's really dependent on how frequently our timer interrupts occur. But it's the best that we can kind of do reasonably efficiently. Okay, so now it's time to evict a page. What do I do? Well, if the access bit is 1, my decision is simple. It was accessed since the last timer interrupt, so I know it's part of the working set. So I just go ahead and clear the access bit and move on to the next page. If the access bit is 0, then I have to think a little bit more carefully. In the past, we would have just said, okay, we found our page to evict. But WSClock tries to say, well, if that page has been accessed recently enough, then it may still be part of the working set. So it looks at the time of last use. And if the time of last use is within tau of the current time, then we go ahead and skip it. We say it's still part of the working set. So it's just trying to add a little bit of sophistication to the consideration of each page. If we come across a page that doesn't have either of these things, so time of last use is far enough in the past, and the access bit is 0, then we say, okay, that page is outside the working set. We can evict that one. Okay? And now we have another interesting question, because the page may be dirty, or it may be clean. So this is where, LRU enters into the picture. Now we have a decision to make. So WSClock tries to be a little bit more clever. So basically, if we have a page that's dirty, we don't want to evict it because we know that we're going to incur a write as well. That's pretty lame. But I do know I need to write it eventually, so why don't I go ahead and schedule that write to occur and then keep looking. Maybe I'll find a clean page, and then I'll use that clean page instead. And again, how long is the write going to take? Well, it's going to take hundreds of thousands to millions of clocks, so it's okay to keep looking. Maybe I'll take 200, 500 clocks and find another page that's actually clean, and then I'll use that one instead. Okay? So if I find a clean page with a 0 access bit that is been accessed further than tau from the current time, then it satisfies all my constraints. I'm going to use that frame to load the page. I'm going to just use it. I don't need to evict anything. Okay? So, again, we have this interesting bias against writes, because they are slow, that we have pulled from NRU. Okay? Now, by the way, I'm not just pulling this out because, wow, what a weird beast. It's like a Tasmanian tiger that looks like multiple animals that have been stitched together. It's like a lot of discussions of paging policies talk about WSClock, and so it's kind of an interesting algorithm to consider, just because, and it really does clearly illustrate how these systems frequently stitch together multiple approaches to try to be clever. Anyway, so that's justifying the slides, I suppose. Anyway, so the question is, we have a way of handling pages that have been accessed. Okay, we don't evict them. That's fine. I'm sorry, pages that have been accessed, pages that haven't been accessed, but we still think are part of the working set. And then we have supposedly this magical collection of pages that are not in the working set, maybe clean or dirty. But we still have situations where we may not actually find a suitable victim at that point. So we have two possibilities that could have occurred. One is that we did find pages that could be candidates for eviction, but they were dirty. And so we scheduled some write back to the disk. Well, eventually that write will complete, and I'll just keep going in a circle looking for a frame, because that's what computers do. They don't get bored. And finally, eventually, I will come across a page where the write has completed, and it will now be clean, and I can go ahead and use that now as my frame. So that's one possibility. You can see that's a slow one, but you kind of have no options at that point. Interestingly, we're saying that this working set constraint is a strong constraint. We can't shrink the working set just because we can't find any clean pages that we'd like to use. So it would rather wait to finish the disk access than to shrink the working set size, which is kind of interesting. Okay, the other possibility is that we have no writes scheduled. And so that kind of implies that everything is part of the working set. Okay? No writes were scheduled because everything was clean, but everything that was, if we found a page that was clean that we could use, then it would have had a time that was not within tau, so all the times must be within tau of the current time. Rats. So we just pick a page and evict it. Okay? So you can see that we degenerate into just random behavior or something like that if we don't have any of these good situations occur. All right, so that's the working set clock policy. Any questions? There's a few other policies that also try to take working set size into account, but recently we haven't really been focusing so much on those kinds of strategies in our page replacement. Okay, so I mentioned page buffering. This is a little bit of an aside, because so far all of these policies are okay, but they certainly break down in certain situations. And so page buffering is a great way of mitigating poor decisions by paging systems. The first reason why is because we would like to maintain a pool of available frames. What's better than having a system that knows how to evict things when I need a page? Well, a system that knows how to evict pages before I need a frame, so that when I need a frame, it can just hand it right over. Okay? That would be really cool. And the operating system can be clever and keep the I/O subsystems maximally utilized to be writing out dirty pages and blah, 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 trying to reclaim frames so that we just have a pool that we can use. Okay? The other thing that I'm just going to mention as an aside is that sometimes you have to have the OS do this stuff because you may have an interrupt handler that needs a frame. And what happens if the interrupt handler needs a frame and there's no frames available? Well, you can't evict a frame because that would make the interrupt handler block. So the interrupt handler just fails to do whatever it was supposed to do. So you have these kinds of situations that can occur as well. So this is another reason why operating systems really like to keep an available frame pool. And they may even be more aggressive and keep a pool of frames just for interrupt handlers to use in cases that they're needed. So just be aware of those kinds of details as well. Thankfully, we don't have to think about any of that in PINTOS. Okay. So basically what these OSs do is they will periodically try to reclaim pages that look like they're unused. Let's say that what we did instead is, let's say that we implemented the aging policy and we just said anything with a value of, let's say, 8 or less, we're just going to take back. We're just going to take it back because we think you're not using it anymore. And that will go into our pool of candidates for eviction. Okay, so again, this is not an eviction anymore. It's just we're staging you for eviction because we think you aren't being used. And so when we have candidates for eviction, again, we have two scenarios we have to think about. We have pages that aren't dirty, and we have pages that are dirty. And so we need to think about which one of those situations might be the case. So if we have a clean page, we put it into a page of candidates for reuse immediately. Okay? So those would be for faults, because we can use them right away. Dirty pages need to be written out. So let's cache them up and then write them all to disk in a batch. Okay? The OS can schedule that in an efficient way. The disk controller can schedule that in an efficient way. And so we'll just try to take care of a whole bunch of dirty pages at once, and then we can move those pages into the clean page pool. Okay? That makes sense so far? So we've got these pools now that are being managed by the operating system. And this is where it's really nice that if we have a simplistic scheduler that's not able to make good decisions, and it turns out that that happens, basically, as long as that page has not been reused to load another, as long as that frame has not been used to load another page into it, it will still have its old data. So if we have a fault on that page, we could use that page. We could just reassign it back into the process that faulted. So this is really neat. We said we think you're not using this anymore. We turned out to be wrong. The process tried to access it again, generated a fault, but hey, we have it cached away here. We can just plop it back into the process's page table, and then it can be utilized with hardly any cost. I mean, yes, we generated a fault. Yes, we lost a few hundred instructions, but that's a lot cheaper than actually loading it from the disk. DEC turns out to have a lot of issues like this. It's funny because the DEC Alpha is the processor that doesn't actually support read ordering unless you use fences, which, because of its dual data cache on the processor that isn't kept coordinated. They also had another issue where their page tables didn't update the access bit correctly. Okay? The dirty bit was updated correctly. At least that worked properly. But the access bit wasn't updated correctly, so VMS couldn't really use the access bit to implement a more clever policy. So it just used FIFO. But it had a page buffer, so that if FIFO said, you know what, I think that this page is ready to be evicted because it got loaded a long time ago. I don't know if it's been accessed because I'm blind in that way. And it finally gets to the front of the queue, and VMS says, okay, it's time to evict you. Well, it's put into a pool, and if the process turns around and tries to access it again, it can be pulled out of the pool. Okay? So this was an approach that was used to sort of mitigate the generally disastrous policy of FIFO in a real operating system. So it's one of those interesting details that this page buffering can actually be really helpful. Okay? Any questions? All right, let's see. So I think I'm going to actually skip this part about emulating the access and dirty bits because we actually do this now in CS24. But the reality is that not all processors with MMUs actually emulate these bits. They actually provide these bits. ARM processors are a really notable example of that. So any modern smartphone probably has an MMU that doesn't emulate these bits or doesn't provide these bits. So the OS has to emulate them separately. And so you can read about how that is done. It's really straightforward. You just use permissions to tell when a page has been written to, because you generate a fault if a write occurs to it. And you can also unmap and then remap pages to detect whether it's been accessed. So that's what is done in the CS24 Virtual Memory Lab now. So we don't really need to spend much time talking about it. Okay, And yeah, if you look at the Android Linux kernel, which you can actually access because Android shares that kind of stuff, then you can see the way that Linux actually emulates that on Android. So it's pretty cool. Okay, let's see. There's a few other things. There's one other thing that I want to talk about, which is this whole thing of frequency versus recency. I was talking to some of the students after class last time, and it turns out that least recently used is bad in some situations because you'd really like to look at frequency as opposed to recency. Other times, frequency information is much less useful than recency information. And so you have these situations where you kind of need to balance the two. And so LRU policies is just a term used to describe, well, when did the last K accesses occur, as opposed to just the most recent access. So you look at the kth most recent access in the past. Okay, so LRU2 is a really common example where you look at the second most recent access, not just the most recent access, because that tells you a little bit more detail about whether a page will be used frequently. So again, you're balancing recency and frequency information. And so LRU2 can actually outperform LRU in certain situations. Now, other ones, LRU outperforms LRU2. So how would you trade off between the two? Okay, so this is where this really clever replacement algorithm was developed, trying to combine these two ideas. There's actually another one that's even better now than ARC, but I just wanted to mention this one really briefly, which unfortunately is patented by IBM. All the really cool algorithms get patented by companies, and then you don't get to use them in open source software until like 20 years later, which is annoying. But anyway, you have two queues, an LRU1, which is for pages that are only accessed once, and then you have another queue for pages accessed at least twice. And so that's going to be the LRU2 information. And the queues have two regions. Okay, you have a top region, which contains pages that are actually in memory, so they occupy some frame. And then you have pages that are in the bottom portion, but interestingly enough, the page is not in memory anymore. You evicted it. So basically what you're representing is past decisions. These ghost entries say, this was a page that was in memory, and I evicted it. But I'm keeping around the detail that this page was in memory, and I decided to evict it. Okay? So how is this used? Well, basically, if a fault occurs, and it's a fault against one of these ghost entries, then I can actually tune the sizes of my queues. So if I get a fault against L1, for example, the most recent access, where I only consider the most recent access, I can increase the size of that cache. Or if it's a fault against a ghost entry in the L2 cache, then I can increase the size of that. So basically, I can tune back and forth based on program behavior what would be the best approach, what information I should consider most for making my eviction decisions. And so this adaptive replacement cache approach really kicks LRU's ass. That's the technical term for it. Okay, so it can use the same cache size and well exceed LRU's hit rate as far as avoiding faults. So that's a pretty cool thing. And I mentioned here CAR, which is ARC, but slightly different order. And CAR is a patent-free implementation of ARC. Similar idea, different enough that it doesn't actually need to, there's no patent burdens that you have to concern yourself with when you implement CAR. So you see that in some places. And like I said, there's another one which actually is way better than both ARC and CAR. And I don't remember what it is off the top of my head. I have the paper saved somewhere, but I haven't read it yet. So anyway, so there's a lot of interesting advances occurring in this caching arena. Okay, so next time we'll go ahead and we'll talk about cache, page allocation policies, and we'll try to talk about a few other things that might help with the assignment as well. So we'll see you all next time.